Welcome, everybody. Today is September 13, 2024. I'm Paolo Cassano. This is the MGH brain-PBM clinic round. It's my great pleasure to invite today to speak Dr. Julia Scott, the director of the Brain and Memory Care Lab at Santa Monica. Julia, thank you for being here, and please take it away.
All right, thank you so much for hosting me today, Paolo. And it's really a privilege to present to the group today. And what I want to share today is kind of the beginnings of our research in the lab around transcranial PBM. And I'm coming to this from the perspective of a neuroscientist, neuroimaging in particular. Many years of doing MRI and MRI-type neuroimaging and longitudinal models of brain change. And the last 7 years or so switching over to EEG and other measures of functional brain activity in the context of health applications. So that type of work built together what we now call the Brain and Memory Care Lab, which is part of the Healthcare Innovation and Design Program at Santa Clara University. And so the collection of my research is around using technology and non-invasive approaches to support brain health. So in the full scope of what we do in the lab, it includes the use of extended reality technologies, EEG as a measure of brain activity along with other biosensors, for heart rate, breath, and so on, exploring the use of photobiomodulation for issues around the aging brain.
Precauciones, sobre todo si ustedes son de los que van a salir del puente a lo largo del día. Aquí tienen las imágenes de las inundaciones de este jueves.
So the focus for today really is on the neural correlates for transcranial PBM. And the studies that we'll be talking about today are really focused on the healthy brain as a starting point. And when we moved into this area of research, it actually began with inquiries from Marvin Berman of the Klein Foundation, where he was seeking a better understanding of real-time neural correlates that could be used in clinical practice to guide the treatment protocols as kind of the real-world application. And as we explored that problem area, one of the things we realized needed to be built was an actual device and system to simultaneously measure EEG and while delivering photobiomodulation. And so that was really our first objective that has taken, we're on our third year of developing those prototypes. So I'm going to show a little bit about that and the potential for that to build a research closed loop system for research purposes, to better understand how to refine those protocol parameters and to be sure that we're actually modulating brain activity in real time and have that ground truth first before thinking about what the clinical integration may be. And the second study that I'll be talking about is a collaboration with Neuronic. And Neuronic is interested in similar questions of those EEG correlates, those EEG biomarkers, related to the use of their device design. So in the second study, that is using research-grade EEG in combination with a commercial device. And what we're looking for there is basically an indicator that there's sufficient amount of energy reaching brain tissue to change its activity. So those are kind of the main objectives here and the scientific questions that we're exploring. So as this audience knows, the same slide I put on all the presentations, but as audience are experts in this, PBM has promise for recovery in neural injury and neurodegeneration. There are plenty of studies showing clinical evidence of that. What is still in exploration is optimizing those protocol parameters. And that's kind of where these questions are. And as far as I can tell from the field, and if there's other information, please, this is coming to you guys to get more guidance. There aren't really standards for dosage parameters based on biological metrics. So this is kind of building up to this so that we may exploring the use of EEG as that within session indicator and leading in that broader vision to an adaptive PBM system. Okay, so when we think about PBM to scale, that's you've met near-infrared light. The more affordable way to do that and to get full head coverage is with LEDs as the light source rather than lasers. The challenge here in the delivery is that attenuation of the signal and the likelihood that greater than 99% of the energy is lost before it even reaches the brain. Where you also have from the animal and in vitro studies that you need about 2 to 4 joules per centimeter squared in order to get a neural response and get that cellular response that has the therapeutic potential. And one of the, so we have this disconnect between how much energy can start at the source and what actually needs to get to the tissues to have any effect. The other challenge out there is that the ion channels that may be responsive to near-infrared light, the TRPV channels, in the human brain are not widely expressed in the cortex, which is really the only tissue that is possibly reached by tPBM in the human condition in that model, which is very different than doing these experiments in the mice where that light and the energy has the potential to reach those deeper regions of the brain that actually do express TRPV channels in any density. So when we look at the LED systems for tPBM and looking at that range of 850 to 1070, most of them have an energy output at what I've seen 40 to 75 milliwatts. And in order to get to that greater than 2 joules per centimeter squared, the calculations for that fluence, it takes either a very long time looking at our exposure or really overlapping putting the density of the diodes together so that they overlap and reduce the effect of that scatter and accumulate that energy. But when we start to modify the parameters in that way in the actual application, then you have these issues around, is it actually going to be usable when you consider how much time someone has to use it, the heat accumulation, and the overall comfort for the person who in the real world application will have some type of brain injury or neurodegeneration, which is going to make a compliance even more difficult. So this comes back to what are we going to do about this, or how are we going to understand, right, where the mechanisms or which mechanisms are actually modulating the clinical outcomes. So while we do see those effects on cognition and thinking, mood related to neuropsychiatric symptoms, we also see from the biological perspective that there are cerebral blood flow changes that are acute, functional connectivity changes that can be seen over a clinical intervention. But both of those things, the cerebral blood flow and the functional connectivity, don't necessarily mean that there is an acute real-time response from the brain. It may be an adaptive plasticity over an extended period of time. And when we look at very controlled experiments with lasers, you do see that neural response. There's evidence there. as we've seen in the very recent studies in the last few years published showing this really clear evidence that the brain can directly respond. But in all of these experiments, in that pulse stimulation that's looking for the entrainment, the stimulation is at a very focal region of the brain, and then looking at the response across the entire brain. And in these experiments from Humming-Liz lab and Pruitt, you see that alpha entrainment can be detected with a 10 hertz stimulation with relatively short stimulation period. So 4 to 8 minutes or 6 to 8 minutes typically, and looking pre and post and making the comparisons. So you see an increase in the alpha here, and in this experiment with that most recent one with the combined MEG and EEG, and modulation in the beta range as well globally. Looking at this from EEG from an ERP perspective, that task space, again, a focal stimulation that is targeting the cognitive process involved, and you're seeing a change in the ERP signatures. So the potential is there. The question is, can we see this with an LED system? Okay, and what we do see with the LED systems, which of how many of these is it actually targeting? And really that question of, can there be that direct excitability? And if there is that direct excitability, we should see short-term EEG response as seen with the laser studies. Okay. And so this is just showing where the target channel, those TRPV channels, and the very clear evidence from animal studies about the oxygenation changes and blood flow changes. Okay, so let's get into what we've been doing in our lab in response to the research this community has done to guide our questions. Okay, so in building this hybrid system, we started with how are we going to build this into how we're going to build this as programmable modular units as a research tool that can be highly parameterized in how we control them. And so what we have designed are these units that are approximately 3 by 4 centimeters, where we can load, in this version of it, a 6 by 6 array of diodes. And we have panels that are 850 nanometers and 1070 nanometers. In previous iterations, we took the same size panel and packed it with 96 diodes just to see maximally what we can do. And when we packed it with 96 to kind of maximize the total source energy, we had major hit-eating issues, as you would imagine, and the power demands were very high. And so in our iteration this year, we reduced that to the 6 by 6 array so that there is spacing between the units, not as much heat generated, but still have an overlapping light field that we know with the specifications for these diodes, there will not be gaps across this 3 by 4 centimeter area. The other aspect of the design in these boards that we wanted to be modular, so we can put these at our prescribed area of the brain, is that we can put together as many as we need. And so the boards are connected in a daisy chain manner, in that serial manner, and very easily taken in and out. So if we look at this on our prototype, we've been putting these diodes, these panels, these modular units onto a ultra cortex frame from OpenBCI. And the reason we did this is because the frame has these natural gaps in them with this honeycomb design, and this is where we can place the panels. And in terms of how we adhere them to the frame, it varied from prototype version with each iteration. But the way we've been doing this prototype right now to mount these in here, or we can put them about 11 into this and still power it on 12 volts, or up to 12 volts, is by using the think pulse electrodes, these dry electrodes here, that have this bulbous unit around it. And simply what we've done is use elastic bands to loop it around the electrodes. And so we can place these in those interstitial spaces between any combination of electrodes that we put in, so that where we measure the EEG activity and where we're stimulating is in proximity. And so what you're seeing here is a setup with 8 electrodes. We have the capacity to put 16 electrodes onto this device and up to 11 of these modular units. Once these are in this position, in that close proximity to the electrode, they're actually a similar offset as those electrode prongs. And so we have the light source 5 to 10 millimeters from the scalp, which is closer than many of the commercial devices out there. So minimizing that scatter before it even reaches tissues. So when we have the electrodes in this position, this allows us to gather intermittent EEG activity that is regional. What we can't do because of harmonic interference from the pulse stimulation is read the EEG data during the stimulation, but we can turn the stimulation on and off to get packets of EEG recordings. In order to get the continuous recording of global brain activity, we have used in-ear sensors that are far enough away from the panels that they do not have that interference, and we can at least get a continuous global signal without any interruption. So then in designing our control system, the goal here was to have a relatively simple system that can go from both an open and a closed loop design. And at the moment, it is still an open design, an open loop. We haven't yet gotten to the point of the closed loop because we're working on those metrics. But on each of those panels, we can control each column, so 6 diodes at a time. And then within that, each diode can be controlled for duty cycle, frequency, and duration. And with the control of each of the array columns, we can modify that stimulation pattern across the panel. So this really gives us, and on top of that, when we have 1 to 11 panels, we can turn on 1, 5, 7, whichever combination we want because of that daisy chain approach. And so this is highly modifiable as a research tool. We're using a simple touchscreen interface to input those parameters, and we've programmed all of this through the Arduino boards. Okay, and so after we've built this, we tested a variety of protocols on both the 850 and the 1070, and because of this little simple elastic mounts, we can readily switch out the 850 and the 1070 boards. Looking at starting with the diodes and building those boards on our own, these are all knowns, and so we can get good estimates of what the radiance is and what the fluence would be for the system we've designed. And starting with those knowns is critical as we're building this research system, where we want to know at what point are we getting sufficient fluence in order to get a neural response. We tested 2 protocols, one a continuous stimulation pattern, and at 6 hertz. We did not test at 10 hertz, which is typical, because we did not want the issue of eyes open or eyes closed or other cognitive processes or states that are highly modifiable by alpha to complicate the detection of the stimulation, the responses to the stimulation. the protocols were typically delivered in 5-minute intervals, so 5 minutes being our minimum. And in the when we use the think pulse electrodes, the dry electrodes, that it was 5-minute stimulation, 1-minute recording. In your EEG, we would still follow that protocol, but also I'll show you the results from a test of just 30 minutes of uninterrupted stimulation at 6 hertz. Okay. Based on the parameters of our system, we have these estimates of the fluence, and the really having a reduction in that fluence when we move to the pulse stimulation, which is again one of the most common ways of using the LED systems versus the continuous, because the LED systems are trying to target that entrainment, but you do get this loss in that power. And in this example, I believe the duty cycle was at 50%. Okay, so we ran a lot of validation experiments here with our sensors and with our protocols. And when we use the in-ear, the IDA and Guardian systems, we first tested those new systems because these are new on the market. We got the first batch from the manufacturer, and we needed to make sure it was actually picking up global signals, real global signals. So we ran the typical standard tests of eyes open, eyes closed, looking for that alpha signature, which we were able to detect. And in addition, we did the stress test that should modulate alpha based on the cognitive load. So we did the Montreal imaging stress test, which has you do more and more complicated arithmetic in your head. And as that goes from very simple things that any third grader can do to much more larger numbers, multiple processes or multiple operations, that's considered a high stress condition. And what should be seen, the standard measure there, is that decrease in alpha. And we're able to see that really clearly every time we ran it. So if you see this mauve color, this is the alpha and the low stress condition, and then switching over to the higher stress condition of the more complex math, you see this suppression of alpha at that global level. So between the eyes open, eyes closed, the stress test, and other standard evaluations of when you look at new EEG systems, we have confidence that the in-ear system is able to detect global state changes in the brain. Okay? And so we initially did this with the 5 minutes, the very short term, and we were not seeing any response in that target frequency range. Went through that numerous times with numerous people, and we're really just getting random fluctuations in brain activity under those rest conditions with the 6 hertz and the continuous stimulation with the system we designed. And at the point of doing this test, we ran it with 6 panels over the top of the head. So not just one point area, but also acknowledging we did not have full head coverage yet. The build of the additional devices, additional units has been done over the summer. And at the time of collecting this data, we had 6 complete in both 1070 and 850. And the results look the same in both the 1070 and the 1070 and the 850, where during that stimulation period, pre and post, we're not seeing any clear EEG response. In the sample I've shown you here, this is from the in-ear, and we're stimulating in the alpha range, so this orange color or pink orange color, which is this line here. And you can see the fluctuations, and this is a z-score, so this is normalized. The fluctuations in theta range are not shifting with this extended duration. So in this maximal condition, we just put it on for 30 minutes straight, no interruption, and we're like, if it's going to accumulate enough energy in the, this is the situation it's going to do it. Without going over 30, thinking, well, then at this point we may begin having heat issues. And so this is an exemplar, but all of the pilot data we've run across numerous people look really similar. And in terms of the 8 electrode setup, that did not show anything different. And I'm not showing that here. That data is a little bit noisier overall as we're working on optimizing that electrode system. But we didn't get any indication from that there were regional effects. So this is starting to put into question, are we really getting a sufficient amount of energy going in? So what we're going to do next is really try to maximize the delivery of from the LEDs. So we finished building the 11 panels for both 850 and 1070 over the summer. We're going to go back to optimizing that intermittent protocol with the 8 channels to look for regional effects, and looking at other measures of related to blood flow. Related to blood flow at both the skin level, and then if we can find the proper collaborators, who might be in this room, doing an FNIR style study to look at cerebral blood flow changes. The other variation we can make is rather than doing a rest condition, create a stress condition and or another sort of stimulus to probe the changes in brain activity. So that's where we're at with the first phase of building this prototype. So you can see we have some fundamental questions to still answer before we can get to the point of a closed loop system. If we don't have those clear metrics of a response, we cannot move to the next steps. So next I want to summarize where we're at, and that all of this is work in progress with the use of looking for EEG biomarkers with a commercial system. So the system we are using is the Neuradiant, and the Neuradiant, it has a rigid shell design with an array of 256 LEDs that cover much of the head, though not all, pretty much all of the top of the head. In this version, we have tested with both 1070 and 1040 nanometer diodes in the device, and the current device is at the 1070. So you can see by looking here that the distribution is fairly even, and the spacing between these diodes is approximately 10 millimeters plus or minus. And what we can look at here is kind of quadrant level distinctions in that stimulation and levels of control. The control system here has 4 regions. We're able to modify the frequency and the duty cycle at 4 levels, where at the highest level it is continuous, and we can bring it down to 25%. So we have played around with those variations in our different experiments. And again, this also has a maximum duration of 30 minutes on the device guidance. So how do we actually set this up if we're going to be measuring EEG and stimulating at the same time? In order to make that happen, we had to be very deliberate about our EEG choices. Okay. What we chose in terms of our EEG system is the ANT Neuro Waveguard Net. And the reason we chose this system, and a relatively sparse 24-channel system, it was so that we can we minimize the obstruction of light coming from the device, coming from the Neuradiant device. As you can see, there's that mesh design leaves a lot of open space. The saline sponge electrodes are about, again, 8 to 10 millimeters in height. And with the design of the Neuradiant device, it actually doesn't add much to the offset as you're putting this on. It does add a little bit, but at the end of the day, we're still looking at probably maximally 20 millimeters away from the scalp in this situation, coming from the source of the diodes. So we have the cap put on, then we put the neuronic device on before we start any of the recordings. We've also run these experiments with that in-ear system that I mentioned earlier, which gives us the advantage of being able to measure EEG continuously without electronic interference. And I believe we only ran like 1 or 2 sessions with both on. You can imagine for the participant, once you put all this on their head, they're a little bit uncomfortable. So let's take a look at what we learned here. Taking a look at our protocol. What we're able to do, get 5 minutes of baseline, do those 5 minutes of stimulation, record, stimulate, record, and we can repeat this. We repeated this up to 4 cycles of the stimulation, and getting an extended pre and post with eyes open and eyes closed. The setting that the person was in was a rest condition with ambient music, natural lighting, and some variants, especially during the longer ones, we needed to have some sort of cognitive engagement, so people watch nature videos, because it's very hard to get college students to sit still for 30 minutes and not reach their phones. So that's where we're at with this. These are the control parameters and our expected responses to the particular stimulations. So in this variant, we did use a 10 hertz stimulation in the pulsed at a 50% duty cycle, and we're expecting to see an increase in alpha as our candidate metric. On the continuous condition, we're expecting to see the theta beta ratio shift downward, and to control for that theta beta ratio, to control for the inherent difference in power between pulsed and continuous. With a pulse being at 50% and the continuous at 100%, you're inherently delivering more energy. We designed a proxy continuous condition. And so again, same duty cycle as the pulsed, but at a very high pulse rate beyond biological range. So it should function like a continuous stimulation and have a same sort of shift in that metric, okay, while delivering the same amount of energy density as the pulse protocol. And these we have run in pilot studies, 6 different people, some people having multiple sessions and trials. So we're still at this pilot phase looking for those signatures. For the analysis, we use the M&E libraries using standard methods for filtering and quality control, and following through to a PSD analysis that have been done both per channel and globally, absolute and relative, in order to explore these candidate metrics with the goal that these can become tuning parameters for the stimulation protocol. All right, so these are sample individual data, but it is representative of what we're seeing. And what we are really seeing when we look at these absolute values, just to point out, top column is I thought I fixed this. look diagonally for the common EEG channels. So the 24 channel is this one and this one, where we're looking at the average across all the channels. And then the in-ear are these two panels. Apologize for not fixing that. I thought I replaced this one. Where we're looking at those global metrics. So again, these are global metrics. This is with pulsed and continuous, and the proxy continuous looks similar with the data not shown here yet. But what we're not seeing, and what we would expect to see, is that in these intermittent zones, between those gray blocks, or the gray blocks are where we have the stimulation, we would expect to see a shift in those values. If we look at the pulsed, we would expect to see a steady increase in the alpha frequency range. And as you can see with this red line in this run, we're really not seeing any change, and this is consistent with all of our trials. And looking at this with the in-ear, again looking at the the blue line, we are not seeing that change. So again, we're working with a different system, a commercial system. In the pattern of use, it would typically be used, and we're not seeing a clear EEG signature. So what do we do with this? First of all, this is kind of telling us that we really need to look more closely at the design of the systems, from the form factors to the protocol parameters, in order to build something that will sufficiently deliver enough energy. The other thing this may hint at is that even if we are delivering sufficient energy to I'll say broadly, the head, the changes in brain function that are observed may be due to those indirect effects of the known mechanisms of PBM through the immune system, metabolic responses, and circulation. The other possibility here is that the pre-post outcomes observed in the clinical trials with neuroimaging markers may be due to those systemic effects that generally support brain health, that allows it then to improve in its function, rather than a direct stimulation of neurons or glia leading to changes in brain activity. So wanted to leave that as possible explanations for what we're seeing as we wait to explore a bit more. We're not done yet. So really what we're doing in the next phases is expanding the candidate metrics to connectivity metrics, looking at those network effects with the ANT neurocaps, and working a little bit further with the continuous pulsed, proxy continuous, and modular stimulation protocols in healthy cohorts. So there's still a possibility there of that we want to explore more. And then the other possibility of changing our experimental design is actually, like we mentioned earlier, adding a probe, as was done in the Pruitt studies and the Zhang studies, looking at working memory and processing speed alongside other systemic measures that will change in response to blood flow. So if we add in measures of blood pressure and HRV during these cognitive tests, we would know what expected change in behavior and cognition, and looking for that neural signature. So that's what we have coming up. See, and what we would really love to work towards is this concept of a closed loop neuromodulation system in order to improve the actual delivery of this type of therapy. Thank you so much. This was all done at Santa Clara University, collaborating with Dr. Sally Wood and Dr. Andy Wolf from the Electrical Engineering Department on the design of those prototypes and some of the analysis. Akshat led the studies with the Neuradiant device and developing the analysis protocols and working with Nick Seemenger. Mike Greenkamp and Kara built the prototype device that you saw in this generation, redesigned the circuit boards, and is working alongside student Karis Ha in the experimental phase of running these studies. I'd like to thank Neuronic and for funding some of this research. Thank you so much.
Thank you so much, Julia. I mean, this is a really pioneering work and very exciting to be able to have both shedding the light and measuring in real time. So I'll open it to discussion. If people can actually raise their virtual hand, I cannot see everyone at the same time in the screen. But apparently there are already some questions in the chat. Is it possible that a difference in time constants of response at the level of individual neuron between, say, 1070 and, for example, 850 due to difference between TRPV simulation and CCO stimulation might affect short-term response?
Yeah. I can respond to that a bit. And so I think I know it's getting at the 10. One of the reasons we designed our prototype with both 850 and 1070 is because of the background research that shows that they are targeting different proteins, basically. So we will be able to make that comparison. And the TRPV receptors, those channels are more likely to be responsive to the 1070 based on what I've read than the 850. So there's value to, as the community knows, to both. And part of why we want to build systems that can be interchangeable and still have the same control system. The other aspect of the prototype system we devised, it has the power control is modifiable. So it's not a fixed brick of 12 volts. It is the system we can adjust from 5 to 20. So that gives us the ability to work with different diode systems. Yeah. Does that answer the question?
Marty?
Right.
Yeah, apparently. And Leon?
Hi. Thank you for the amazing talk. Your results really, they mirror what we have been observing in clinical practice, where just the use of the TBM doesn't really change much. The EEG is when you really add a neuromodulation technique like a non-invasive brain stimulation, that it seems that it really changes the power of the EEG. And it really makes sense based on there is no polarization of the membrane with TBM, right? So have you considered, you are exploring other metrics. In some clinical cases here at the hospital, we've seen clear changes in tissue oxygenation measured by FNIRS after photobiomodulation. Those changes are not captured with EEG. We just observe that with FNIRS. So are you considering something like that as well?
That's part of what we would like to do next. And coming to this group is part of that, that ask of how we're going to get to the next phase of looking at these other physiological responses, and that the cerebral blood flow changes or the skin blood flow changes is one of those metrics we want to add into the protocol. At this time, I don't have those tools in the lab, so we need to find a way to get them in and run those studies here.
Funding. It's always funding the program.
Yep.
Thank you.
Okay.
And Attila, I know you have a question. If you want to ask your question.
No, I think it was more of a rudimentary question. I was looking at the timing of the in the table where the stress condition and the rest condition were that hours were, one of them was at around like 6 p.m. if I'm not reading it incorrectly, and then
Yeah,
11 p.m. with
yeah.
different. Is that
So
time of the day? And if so,
it's
yeah.
yeah, it's real time, but the one of the so yes, they were done at different times of the day. We did not control for that in our pilot studies, but it is not at the times you see because the with the Ivan systems, their clocks are still set by Swiss time because that's where the company is. And so when we record on their system, it's still in Swiss time, and we're in California, so we are not running experiments in the middle of the night. So, yeah. But we, as we move forward, and we're getting out of the pilot phase, controlling for time of day and circadian rhythms is of course relevant. Yeah.
And Lee?
Hello, this is Hanli Liu, and thank you for citing some of our previous papers. And I really think your, what do I say, integrated system between EEG and LED together that has a huge potential because feedback loop, as you say, closed loop is really promising and great, and that's needed. One thing I want to make a comment about EEG signal is that according to our own experience, even with the MEG, the signal changes are really weak. And then you can't just by looking at it and say we see the difference between pre and post. And also just a few subjects would not allow us to see any kind of a statistically meaningful difference. So that's why I spent years to learn how to deal with EEG data analysis, which basically means we need N equal to 12 or more. Mm-hmm. And also look at a particular frequency band and things like that. So that's why my experience is really telling me that at this stage, you probably need to focus on certain bands with a larger sample size and with simpler tasks, simpler or fewer focuses, fewer conditions. So that's one thing I want to make comment. And I had a colleague who did the animals measurement, and then we published a paper. I didn't really share in this group because a lot of mathematical stuff. But then the animal study that my colleague did, who is going to publish his paper, and our own work is showing that during this TPBM situation, CCO or HBO, meaning hemodynamic signals, are leading the EEG changes, which is something I'm still not completely understand. I don't yet understand that. And then again with Gonzalez Lima back to a few years ago, we saw that, and he would not have a good explanation either. But what I try to say is, EEG signals from TPBM are not giving us a fast changes like we observe for TMS or TDCS, meaning the electrical stimulation or magnetic stimulation will give us a faster changes along EEG signals. But for some reason, this TPBM really gives us a slower changes. And then the paper we published just about a few months ago is showing that during the TPBM situation, we see the reversal behavior, meaning most of the times EEG lead hemodynamic signals, but then in this case, hemodynamic signals lead EEG. So anyhow, I'm just adding some comments, and then
yeah, and
for EEG analysis, you may need more samples.
Yeah, I know.
Okay.
I appreciate the comments, and I was hoping to get feedback like this in guiding the design or the metrics. I know we need more. That's why I keep saying pilot when I'm describing the data so far, and a work in progress. As we go into this next year, that is really our focus, is to hone in the study design. But my communication at this point to the group is that with running kind of this exploratory phase with a lot of different variations, there is not a clear response, even when we're trying to maximize maximize the stimulation and looking at the individual level. And getting a marker that is clear at the individual level is still of importance because of where we're thinking this could possibly go in a precision medicine, personalized protocols, especially when we have, I mean, I'm acknowledging it may not be possible, but what we're trying to design for is keeping that endpoint. You know, we have all these variations in how our heads, our brains respond to this light, everything from our hair color to head size. So having that objective real-time marker is of huge value to know that this is working. So my logic in this process of focusing on the individual things and looking at the simple metrics of the PSD, that if we can detect an individual level change, then that gives us promise for this next phase. Going forward, I've read your papers really closely, and I want to follow more of that approach as we go forward, because it looks like we do need to go and do that group level analysis in order to pick up any sort of signal, and then let's work back to the individual. And I really do want to include other physiological metrics. If getting in the apneas and looking at that cerebral blood flow would be fantastic to round this out. Yeah. Thank you. Thank you for your input.
I had a question as well. So with this discussion in mind, thinking about the issues in terms of signal detection when it comes to EEG and biomarkers, so what does it say about then commercial devices that are using QEEG to personalize treatment? And what challenges they might have, and what precisions we might expect?
So from the perspective of using QEEG to guide the treatment protocol pre-post, that I think what may need to be modified there, like it's still a good metric, to look at those changes over a month period of time, let's say, but looking at that in a acute period of time may not be as robust, but also, sorry, I'm losing my train of thought here. If I think, for this is my opinion, like just not totally founded in working in the clinical setting. I haven't worked in the clinical setting with this, but how that information is communicated to the end user or the patient, and the framing this as this intervention is having these systemic effects on your body, on your head, or so on, something general, and over time there's adaptations that may lead to a change in brain function, versus communicating it as the TPBM is directly changing brain activity. So I think if anything, I may need to be clarified in the clinical or real world applications. It's the way that data is interpreted for the user before anything else, because there's, as we're seeing here, there's still so many open questions about what the effects are and what's
I think this is I'm sorry, I interrupted.
Go ahead. Yeah.
This is a fascinating discussion, and I think that's going to be a discussion that needs to be biomarker specific, because some data already at the level of bioenergetic show that there is specificity in terms of regional changes that you can demonstrate with light, transcranial light. Of course, it's an overgeneralization because it depends on the type of device, the power, all the different parameters. However, I guess back to you on this, and I know we are just at time. My understanding from the literature is that even when you look at EEG, you can see some regional specificity over time of the effect, which argues against the fact that these effects would just be mediated by systemic changes.
And is that with laser-based or diode-based?
Even diode-based.
Okay.
And of course, we'll have to look at the literature specifically, but I know that some groups in the specific QEEG-based modulation field have found that. But I know we are at time. It's a fascinating topic, and I think your data about the issue of the acute change and the usability of that for monitoring and for closed loop are certainly critical.
Thank you so much. Thank you so much for inviting me here, and I appreciate everyone listening and providing their input as learning how to run these studies and make a contribution to the field here.
And I wanted also to thank you not only for being here, but for being able to deliver this talk in this situation at the roadside. This was amazing. Yeah, you maintained such a composure. Incredible.
It's California living for you. At least the sun is shining. Nothing's on fire. So
thank you all. Continue to
Bye-bye.
join us. Thank you for all of you. Thank you.
Bye-bye.
Bye, Julia.